Today we are going to go over the homework for section 5.5, but before that I want to prove the substitution idea for definite integrals, which is on page 589 of your textbook. When I went over this in the last video, at the time I figured this seems obvious and there's no need to prove it. But I've since had this change of heart. I mean, just because it's obvious doesn't mean we shouldn't prove it, right? So let's prove it. It's very short. And let's say let u equal to g of x, and then g prime be continuous over some interval, and f is continuous over the range of g. In other words, the backgrounds are all reasonable, right? Nothing's broken, everything's exists and continuous and that sort of thing. And then what we're trying to prove is that first we're given this is u equal to g of x. What we're trying to prove is that the chain rule, or what the book calls the substitution rule. The chain rule for indefinite integral x dx equals to g of a and g of b, from integral from g of a to g of b f of u du, where all this stuff, where the derivative of f is what is that? G. That's not a d. Okay, let me fix that. What is that? Okay, so this is a perfectly arranged chain rule situation such that the derivative of f becomes the derivative of g of x is g prime of x is set up right here such that by the evaluation principle, that is the same. If you set u equals to g of x, then you can substitute the u. Okay, that's just repeating the evaluation, the substitution principle. The question we are having here is what happens to the definite integral to the nth? Well, you just being that the principle is that, well, why don't you just figure out what u is when x is a, u transforms properly, right? But to prove that concept, let's prove it. Okay, first we go by the principle that the integral of f of g of x by the chain rule g prime of x dx, that is by what we did previously, is the derivative of small f, which is big F of g of x. Okay, and then plus some constant. Now you know this is true because if you take the derivative of this thing, big F, that will be equal to small f with g of x on the inside, and then g prime of x by the chain rule. So that's how you know this is true. Now if we were to integrate this thing simply by adding the limits of integration, or the top and bottom numbers, to make it a definite integral, then we will go by principle. Let me copy all this stuff down again. G prime of x dx. Then by principle, then it follows that this equal to f of by the evaluation theorem is equal to this function evaluated at b, okay, minus this thing evaluated at a. Now that is the same as saying that being that u equals to g of x, so we can plug u in here. That be the same as evaluating u at the value of b, where u equals to g of b. Excuse me. F of u, where u equals to g of b subtracted by u equal to g of a, which is so you just plug the u in because u is g of x. So then that's the same as integrating from g of b, g of a to g of b of the small f u du. All right, so that's just a quick quick exchanging of variables. Okay, so that proves the point. Well, what I end up doing is that when you change variables, then the new variable will take on the value of the old variable according to the formula. That's all there is to it. All right, which you have already done if you have finished the homework. So we are going to go over some of the homework. Let me erase the board. The first problem I want to talk about is problem number 278, where normally if you have something like this, you need to have sign like you need something, the function itself, and then its derivative all in the same place, right? So you have, for example, sine squared cosine cubed in this problem. Well, the derivative of sine is just one cosine. It can't be cubed. Cubed is not going to fit. Similarly, if you were to do the derivative of cosine, it's just sine. It's not sine squared. So then, the thing is, the problem is, we can't use a direct. We can't do just slap on the substitution and call it done. We need to pull a trick, and the trick that the book advises us to pull is use sine squared plus cosine squared equal to 1, the Pythagoras theorem. And so let's do that. Okay, how are we gonna do that? Here's the way I did it. There's probably more than one way to skin the cat when it comes to trigonometric manipulations. But here's what I did, so I'll write that down. We will have sine squared x cosine cubed x dx. That's the problem. And then what are we going to do with it? So we have, I'm going to factor out 1 cosine squared. So then we are left with sine squared x. I factor out 1 cosine squared. So then I have 1 cosine x left. Okay, and the cosine squared that I factor out, I use the Pythagoras theorem. The cosine squared is 1 minus sine squared x. So that's my second step. And then next, I multiply this stuff out, which becomes integral of just this part though. The reason is because the derivative of sine is cosine minus sine to the power 4th x, and then cosine x dx. So the derivative of this one is that thing, okay? And now you have the chain rule set up to be able to, do the antiderivative. So here's what we're gonna do. We'll set up u equal to sine of x, and therefore du equals to cosine x dx. Okay, right? Yeah, derivative of sine is cosine. And then we do, then plug all this stuff back in here. We get u squared, okay, minus u to the power 4th. And the cosine x is just du. And then integrate this way. That's just a simple power rule. And now we perform the integration. The integration says raise the power by 1, so 2 plus 1 is 3. Divide by that power, 3. Minus raise the power by 1, that becomes 5. Divide the power by 5, and yeah, and that's that. That equals to this thing. And then finally, we plug u, which is sine of x, back in there. So we get, we'll write it, well, anyway, maybe we'll simplify a little bit. Okay, u3, that's 1/3 minus u squared over 5, and that equals to u3 is sine 3x. Remember, this power means the whole thing is being cubed, okay? And and then times 1/3 minus sine squared x divided by 5. I need to remember to talk louder. So sine squared x divided by 5. And then don't forget that constant. Okay, is the indefinite integral. We always slap on the constant because the indefinite integral means the antiderivative within any constant, okay? The constant, so it's the entire collection of stuff, but they're all similar. They're just different by only a constant, and that should be yeah, that is. Is there a squared here? Let's see. Wait a second. Yeah. All right, that should be right. Anyway, so that's that. And being that this is an even number, we can't check the answer at the back, but I am confident that it should work out. That should be correct. Now, so next, let's look at problem number 279. Next, let's look at problem number 279, where we are supposed to integrate something called t sine of t squared, okay, and then cosine of t squared, and then dt. Now, when you notice that this is set up very nicely because the derivative of sine t squared is cosine t squared and then multiplied by some kind of t, right? So then that's all you need to do is just that there is some numbering that needs some of these constants that might have to be taken care of. So let's take the derivative of sine of t squared. What is the derivative of sine of t squared? Let's see. Let me look at my notebook. So let's let u equals the sine t squared. U equals the sine t squared. And then du equals to cosine t squared, okay? And then times 2t dt, right? And this is all multiplied together, which means we need to take care of the cosine t squared dt and the t part. So we will move the 2 over here. So the cosine squared t squared times 2t, sorry, there's no 2 here, times t dt will come out nicely, taking care of that, and that. And this one is taken care of by the u. So we rewrite our integral as just u and then du. That's about it, because u is sine t squared, and then du, oh, don't forget the 2 over 2. Okay, and then du over 2 takes care of cosine t squared and the t and the dt. So we just have to integrate this thing, which is equals to u squared, raise the power, divide by 2, and there's another 2, so that's 4. So u squared over 4 is the answer, which we will write it as sine t squared, and then squared, and divided by 4. You can also write that as sine squared t squared, because the square down when the square is down here, it means the whole thing, right? This means exactly that. So sine squared t squared over 4. This is a tradition to write the squares of trigonometric functions this way. And then what? And then that seems like a decent answer. However, if you are to look at the answer of the book, it gives you a slightly different answer. Because that, by the Pythagoras theorem, that is sine squared plus cosine squared equal to 1, this also equal to 1 minus cosine squared t squared over 4, I guess. Well, make sure there's a 4 here, okay? That's the right trigonometric function. So then the integral is equal to this thing or this thing, which means the total answer then is equal to this thing plus c, or another way of saying it is minus cosine squared t squared over 4 plus c, which is, this is the answer that your book gave. I don't know why they did that, because well, maybe they arrived at a different way. I can't imagine. Yeah, they must have took u to be cosine. Okay, that will give you this answer, but this answer is the same as that answer because the constant doesn't matter. We can add any constant. Okay, so these two basically this function and this function are within a constant of each other because of the Pythagoras theorem and for trigonometry. So that's that. Okay, so let's look at the next problem. Next, let's look at problem 282, which is on page 592. The problem with this one is the derivative of this thing doesn't equal to that. See, normally if there was an x on top, then we have a made, right? Because the derivative, if we set u equal to what's inside the radical sign, then its derivative is automatically going to be on top if there was only x up here and instead of x cubed. Being that it's x cubed, then we have to figure out a different trick. And what trick shall that be? What trick should that be? Well, let's call it, I decided to try u equals 1 minus x squared. That is, u equals this everything under the radical sign. So let's set u equal to 1 minus x squared and see if anything comes out. In that case, we'll go through the operations, then du equals to minus 2x dx. All right, and another thing, however, is x squared then equals to 1 minus u, right? So that's how it works out. And we'll plug, and from that, we'll get rid of the negative 2 so then du divided by 2, du divided by negative 2 equals to x dx. All right, so now we have all the parts, and let's plug everything in to see if it fits. So the integral becomes the square root. On the bottom, we have the square root of u, right? Because u is 1 minus x squared. So on the bottom, we have square root of u. On top, we have x squared times x, okay? We'll take x squared times x. So x squared is 1 minus u, and x is, x dx is right here, becomes du over minus 2. And together, that forms, see, x dx times x squared, which is du minus 2 times 1 minus u, together forms the x cubed and dx. So it all comes out. And then now this looks much better. So we'll put a constant in front, and the constant goes minus 2, okay? And this becomes u to the power negative 1/2. We'll just put it radical back into the exponent form, minus u divided by the square root. That's just u to the power 1/2, right? Du. Okay, double checking that I didn't make a mistake. That looks okay. And then that means 1 over half. And then now we'll do the integration. Raise to the power by 1. That becomes u to the 1/2 divide by that power, divide by 1/2, and then minus u to the power 3/2 divide by 3/2. Okay, raise to the power, divide by whatever the new power is. And then, okay, so that's that. So we're doing pretty good. To simplify that, we get some simplification that becomes 1/2 times 1/2. That cancels out. So we get the first term becomes minus. The minus sign is still there. So minus 1 u to the power positive 1/2. It's not negative. And then this one becomes a plus. So plus 1/2 times 3/2. That the 2 cancels out, so you have the 3 left on the bottom. So u to the power 3/2. Okay, that's so far so good. So the last step is we just have to plug the u back in. So that equals to minus u is what? 1 minus x squared 1/2 plus 1 minus x squared 3/2. and then divided by, divide by 3, and that's our answer. And don't forget the plus c, okay? There's always the good old plus c over there. And that is the end of problem 282. Next, let's look at problem 283. 283 is very similar to 282. Well, so I will just tell you how to set it up, and then you can do it just like 282, the previous problem, where you set up u equals to 1 minus y to the power 3, and everything will come out nicely. Then you calculate du and plug everything in, and it will all fit, because then, and you also calculate the y cubed equals to 1 minus u. So that's there's y5 on top, so you have y cubed, and then du is 3y squared. So between the squared and the cube, you get the y5 and make everything fit. And then you work on the rest of it. I didn't finish that one, but it's the it's the substitution part that's most important. Next, let's look at problem 284, which is similar to the one that we just did. So I will just show you what I did. And, well, you have the integral of cosine theta times 1 minus cosine theta to the power 99, and then times sine theta. That is, the cosine becomes, the derivative of cosine becomes sine. That's fine. But the difficult part is in considering there's another cosine there. Now what? And so the trick is, well, you just set up u equals to 1 minus cosine theta, and then hope that everything works out. So then you calculate du, and then the extra cosine theta is represented as 1 minus u. So you plug all that in, and it works out okay. Yeah. What? Give me a second. Yeah. I saw the wrong thing. Yeah, that looks fine. So what happens is then 1 minus cosine theta to the power 99 is just u99. And then you multiply by 1 minus u, which you come out with 2 terms, and so on and so forth. And use the power rule for integrals to come up with some answer. Did I show you the answer? I think so. The answer is at the bottom, and that should be correct. Is an even number, so we don't have the answer, but yeah, if I was careful about it, it should be correct. And if there's a mistake, then you will notice it right away. So 208. Next problem I want to do is 287. All right. Now problem 287 looks impressive, but is not, when you realize what's going on. So look at the problem for a second. You notice there's a bunch of stuff being multiplied together, but the second term, this let's see, this one over here, sine squared theta minus 3 sine squared theta, sine cubed theta minus 3 sine squared theta. If you were to take the derivative of this thing, that's directly this, okay? And without worrying about the constants, the constant multipliers. So then, in other words, you let u equal to that term, and that's what I have. If you set u equals to sine cubed, okay, right here, 287, yeah. So if you let u equal to sine cubed minus 3 sine squared, and then you calculate du, and you realize the whole thing shakes out to become this integral of u cubed du divided by a number of 3. That's it. And then you calculate that, and the answer falls out right away, nicely. So next, problem 299 next, the same principle. What you do is let u equal to natural log of 2x. See, 299, wait for it to zoom in. And then if you let u equal to natural log of 2x, then du is just dx over x, and the whole integral, the complicated looking integral, becomes something simple that becomes the integral of cosine u. That's about it. So it comes out very nicely. Next, let's talk about problem 311, where we're supposed to calculate this integral and show that e equals to 0. Now to do that, we have to pull out some trigonometric stuff. So let's do that. What we're going to do is let u equals to 1 minus t. So u equals to 1 minus t. And then du, of course, then equal to minus dt. All right. Oh, and then the whole thing then becomes, and we need to calculate the ends. So when u equal to 0, when t equal to 0, when t equal to 0, then u equals to 1. And then when t equals to 2, u equal to minus 1. Okay? So we have shifted over. And then, is that it? So the cosine pi of t. Well, anyway, so I think that's about it. So let's write down the new integral. 1 minus t is u. Then t equal to, from here we get t equal to 1 minus u, of course. So then it will become cosine of pi times 1 minus u, and then negative, okay, negative dt becomes du. Dt becomes negative du, and we'll put a negative sign in front. Okay, that's all right, I guess. Or maybe we should keep the negative sign over here. Well, let's not worry about the negative sign for the moment. The point is, now what? Now we're going to pull out some trigonometric formula. This is what? Cosine sum of angles. So let's do that. So cosine of, this is, what is that? Cosine of the subtraction, okay? Cosine of a minus b equals to, that's some rule back from trigonometry. If you don't remember it, just go ahead and look it up, or just believe me. Either way, cosine of a minus b equals to cosine a cosine b plus sine a sine b. This is the cosine sum of angles formula. All right, so knowing that, then we have to apply that to this thing right here. Okay, so then that equals to minus u, and then we'll slap that thing on there, which becomes, this is the same as cosine pi and cosine u pi. So we'll do that. Okay, that is, so that becomes cosine a cosine b, which is cosine pi u. Okay, cosine a cosine b plus sine pi u. All right, and then we have the du back here. All right, so far so good. You might wonder, but why would we think of doing this? It's just a trick in the bag. You don't know how to do this, so you beat around, take out some of the old formulas, see if anything can make magic happen. That's about it. Integration is that way. You know, when the regular rules doesn't work, then you start finding some oddball stuff and hope that it works. And it might or might not work, but in this case, it's going to, because we already know that it's going to be 0, and we're just expected to prove it. So we know the answer is over there. It's like we know the gold is buried. We just have to dig it out. Okay. So and then, so now that we have come to here, okay, there's a parentheses, and then we will calculate that. What is that? That equals to all right, that equals to, oh yeah, we need to worry about where are we going. This is going from from 1 to minus 1, actually, right? 1 to minus 1. Okay, 1 to minus 1, right? When t is 0, u is 1 down here. From 0 to 2, so from 1 to minus 1. All right, that, and then what do we have? And then we'll flip this thing around, because this is that thing is on the the negative value is on the positive. So we'll flip this around and get rid of the negative sign. So the integral becomes from -1 to 1 of all this stuff. And next, we are going to remember something. That is, sine of pi is 0. Lucky us, right? And then, and cosine of pi is -1. Actually, yeah. But anyway, so cosine pi is -1, and sine of pi is 0. So all we have here is just this. Okay, we have minus from the cosine pi equals to -1, and then and the negative sign got canceled out. So we have a new negative sign from cosine pi. So this is just the integral of cosine pi u du. And then this function, wait a second, do I have another u here? Oh yeah, there's another u here that I missed. So let's stick another u here. Now the point, however, is this, that this particular function, actually we should probably just, well, anyway, the point is this particular function happens to be an odd function. That is, g of, if we call this function g, okay, then g of minus u equals to minus g of u. And when you integrate an odd function from a negative value to the positive value like this, the same value, then the integral is 0, and that's the end of the proof. That's why this particular definite integral equals to 0. So that's the end of it, which sounds kind of odd. Well, this function is odd, so that is how you prove it. The hardest part, I think, is just to need to pull out the cosine sum of formula. This is the difference formula, the cosine difference formula, and then yeah, and then stuff comes out. Okay, so that's that. Yeah, I forgot to mention that for odd functions, it looks something like this. Okay, and the reason it equals to 0 is if you integrate from the same distance on both sides, then being that it's odd, the two areas are exactly the same, except one's positive and one's negative. So that's one of the theorem says. As a result, for odd functions, then it cancels out. So let's go to the last problem. The last problem we're going to do, number 315, which says find the area under the graph of g of t, which is t over 1 minus t squared to the power a. A is some number, and we need to integrate, find the area between 0 and t equal to x. Okay, and then all right, where x is between 0 and 1. All right, so x is not that big, which is fine, and a is bigger than 0, plus a does not equal to 1. That's fine. But a is a fixed number, okay? So then, and then we need to find the area. In other words, integrate this thing. And then we'll figure out what happens if x goes to infinity. So what area is that? So let's call the area a. So this is a. The area is a function of x. So a of x equal to this stuff. Now, first, let's look at this problem and not get blown away by too many. There are too many variables, right? There's a, t, and x. But remember, x is fixed for the purpose of the integration. Okay, given each x, like 0.5 or something, you plug it in here and you calculate the area. Well, we don't know what a is, but a is also fixed. It's just some number, and so our result will be something in terms of a. The only integration variable here is the dummy t, and we'll integrate it that way. All right. So having said that, then let's see how we're gonna pull this off. To do that, we are gonna substitute. Okay, area will let u equals to this. What? Give me a second. What? Okay, I did figure out what my notes is talking about now. All right, so let's let u equal to 1 minus t squared. That is what's on the bottom. 1 minus t squared. Okay, and then we'll continue to work our regular plan, which is du then equals to minus 2t dt. Okay, and then you see the t dt there, so we'll get rid of the 2, which means du minus divided by minus 2 is equal to t dt. Okay, and then we have next we figure out the value of integration. Okay, that is when t is 0, because we're doing a substitution, so we need to do the change of the n value, the limits too, the limit, the well, whatever those things are. We need to change it. So when t equal to 0, you have to equal to 1, and then when t equals to x, it integrates to x. At this point, x is held constant. Okay, when t equal to x, then u equal to, well, 1 minus x squared, because we don't know what x is, so we will just write it out that way. Therefore, the area, the a of x, will be equal to the integral of, we're integrating from u equal to 1 to u equal to 1 minus x squared. All right, and then plug everything in. So this is u down here, u to the power a, and then up there we just have t dt, which is du divided by minus 2. Does that look okay to you? And let me double check, make sure I didn't mess up. So that equals to, yeah, that looks okay to me. All right, so let's do the integration. Doing the integration, being that a is not equal to 1, then we can that is, we can apply the power rule. The power rule states that this equals to 1 half, minus 1 half. Okay, we'll put a number in front, and then u will be raised to the power u a plus 1 divided by a plus 1. Actually, wait a second. U is to the power of negative a, right? So it's minus a plus 1 divided by minus a plus 1. And then it will be evaluated from 1 minus x squared all the way down to 1. All right. And so the rest is just going to be some grunt work algebra. But we're going to do that. And that equals to u. What are we doing? Okay, the first one, u equals to 1 minus x squared. All right, so let's write down all that stuff. So that would be, first, u equals to 1 minus x squared to the power 1 minus a divided by 1 minus a. And then subtracted with u just equal to 1. Then it becomes 1 over 1 minus a. And then that's, I think that's about it. All right, so that's our subtraction. That is the area. The area, which is based on x, for each x, this is what the area will be. Okay, that's the right formula. Right. And then the next question is, what happens when when x approaches infinity? Okay, now if, what? Does it really say that? X approach infinity? I thought. Give me a second. Sorry, x does not approach infinity. Okay, x approach 1. That's the question says x approach 1. I don't know why I got infinity on my mind, but we already said that x is between 0 and 1 in the problem. So x is approaching 1, and as you see, as x approach 1, you look at this, then x squared, the x approach 1, 1 minus 1 is 0. And then, then that's 0. Sorry, x approach 0, this approaches 1. okay, then that just becomes 1 over 1 minus a minus 1 over 1 minus a. So the area approaches 0. So the a of x, the answer is a of x approach 0 as x approach 1. And that is the end of the problem. And notice this problem has more variables, so it's a little more challenging. But if you just keep your mind straight, okay, remember x is the health constant here, a is just some number, and then focus on what you're doing. And so x is a constant here, and just keep working on it until you come to the right answer. So that should be it. Sorry, I said the wrong thing. I mean, that's what you get for not checking the answer. When x approach 1, 1 minus 1 is 0. So this does not go to 0. It goes to this thing right here, right? As x approach 1, then it's just equal to this one, minus 1 half times this minus 1 over 1 minus a, which should be 1 half times 1 over 1 minus a. That should be the answer. Now, what's more is that this is only true a approaches this value if the area approaches this value if a is less than 1. If a is bigger than 1, then this becomes a negative value. Okay, when you raise to a power negative, that's the same as division. So as x approach 1, it becomes very small, but it gets to be the denominator, then it gets huge. So it actually goes, I think it goes to infinity if a is bigger than 1. But that detail is not that exciting for us because we're doing integration, not where this stupid thing is diverging or converging. So mostly what we need to focus on is how to do the integration, and then and that's about it. So that marks the end of this section.